So, good morning, everyone. As I mentioned yesterday, today's class we'll go over some examples on how to implement some of the things that we've been discussing in the previous sessions. So, we'll go over basically to start with the same example curves that we used. And I'm going to go over some details on how can we make use of our packages that are already available in order to do some of the analysis that we've discussed. Okay, and then at the end, I'll also show you some explorations on actual data from Brazil. So so that we can look at some of the things that we've discussed on our first session, right? So we're going to have a look on what are the variables that are present in that data set, how do we process some of those variables depending on what we want to look at. So this is basically the outline of this class today. So, yep. Let me see. I'm not sure. There is another way around. Okay. So, first off, this package here, R0, I'm calling just for the sake of accessing this data set that is present there in that particular package. We're not going to be using that, but as you can imagine, it has some functions to analyze a basic reproductive number, but we're not going to go over that in this class. Now, the MEM package, on the other hand, is one that we will indeed not only use a data set that is provided by that package, but also some functions, as we've seen in the last class. So related to identifying timing on a given time series and threshold itself. Okay. And then some other packages here just for plotting, and this is just for code style. Well, not just for code style, but it's required by some of the methods that I will use later on. But in any case, so first of all, the data set that is presented in R0, which is the time series for, if I'm not mistaken, I'm not 100% sure, but I think it's ILI in Germany in 1918, but I'm not 100% sure, so don't quote me on that. But in any case, so it has a particular data structure there, and we're just going to change it into a data frame object. It's a type of object in R that has some properties that will be important when we apply that data set into some of the functions of the moving epidemics method package. So this is just a change in object structure, just for the sake of some of the functions that we're going to be using, nothing more than that. So if we look a little bit into this data, it's just simply we have the row are already named, and you can see, as I've mentioned yesterday, this is daily counts. Okay, so the rows are already identified with the associated date, and on the column you have the number of cases observed at each of those given days. Okay, so just a simple time series. You have the rows could be your x-axis, so time, and the column here. This column just identified the number of cases. Now, in the case of the flu seal data set that we imported here from the MEM package, we have influenza-like cases observed in Castillo and León in several different seasons. So now again, each row now is a week. It's not days anymore, it's weeks. And the name or the index associated with each row, it's already the number of the week associated with the week. Okay? So we have a running year. We start from week 1 to week 52 or 53, depending on the year. And you can see right away that this data set here, it starts at week 40, right? 40, 41, 42, 43, 45, and it ends on week 30-something. Why is that? And we have several seasons, right? We have 2001, 2002, 2002, 2003, 3, 4, 4, 5, until 2008, 2009. So why is it that for this data set, we don't have the data ordered from week 1 to week 52, but instead we have from week 40 all the other way around to week 30-something? This is influenza-like cases, right? And is associated with a territory that is in the northern hemisphere. So when you look into that data, you see that the vast majority of cases, or the period of time where you have usually the peak of cases, is in the corresponding winter of the northern hemisphere. And so it is at the end of one year and the beginning of the other, right? Kind of more or less what we have with dengue cases or chikungunya cases. Usually, they tend to accumulate by the end of the summer, more or less. At the beginning of the summer, we start to see an increase of cases, and it's going to peak around February, March, more or less. So, if we want to define the seasons for those particular cases, it doesn't make much sense for us to divide our data from January to December, because the highest volume will be some part of it in one season and another part of it on another season, right? You will have the beginning of the epidemic phase by the end of one season and the final stage of it on the other part. So your data would look like something like something like that. Now, if we just change how we partitionate our time series, and instead of building partitions on a yearly basis from week 1 to week 52, and instead we look more or less when is the valley on our typical curve, it might make more sense to divide our data set around here, right? So the season will start here, and it went here. Because then, the same information now will be presented in terms of seasons. Like that. Okay? That's the whole point of it, right? So for each particular disease, if there is a clear seasonal pattern, it's convenient for us to divide or to define our seasons in a way that the highest activity is more or less in the center of our season, right? So that the beginning of the season and the end of the seasons are at baseline, okay? So for influenza-like illnesses in the southern hemisphere, the usual yearly calendar is fine because it accumulates usually in the winter, so more or less in the middle of the year. So we're fine. But for dengue in the southern hemisphere or for influenza-like illnesses in the northern hemisphere, it makes much more sense to divide it kind of like starting in August and ending by the end of July, or beginning by September and ending at August, more or less, okay? So that your peak is more or less centered, okay? This is why, for that particular data set, this is what we have. The weeks start at week 40 already, which is by October. September, October. Yeah, something like that. I'm not 100% sure, but I have to check the exact number, but it's something like that, because each month has more or less 4 weeks, approximately. So, any case, we have several seasons there. Each column represents a separate season, and they're all aligned. Now, as we've seen in the examples of last class, let's just start by, yeah, sure. In this case, it's incidence already. It's incidence. It's incidence by 100,000 individuals, if I'm not mistaken, in this particular case. You have to multiply it by the population and then divide by 1,000. Then you have integers. It will be counts, okay? So in the German data set, it's already number of cases, it's counts. But for the flu cases in Castilla and León, it's incidence. So it's number of cases divided by the population, multiplied, if I'm not mistaken, by 100,000 in this case. So it's number of cases per week by 100,000 inhabitants, okay? So it's normalized by the population already. So let's just extract then the first season that we have there. So I'm gonna define a new object here, flusil.2001, which is just the column associated with the season 2001 till 2002, okay? End of 2001, beginning of 2002. It's just the first column of this data set. So we have now a vector that is just the values that are in this column. Now, the exercise that we've discussed on identifying or estimating, given a season, how we can partition that season in its pre-epidemic phase, epidemic phase, and post-epidemic phase. In the MEM package, it's implemented in this function called MEM timing. So what MEM timing does is exactly to take a season or a set of seasons and estimate when we usually have this separation, so the end of the pre-epidemic phase and the beginning of the epidemic phase, and when we have this transition here from the epidemic phase to the post-epidemic phase. Remember, as we've discussed in our last class, this is just the starting point for us to calculate epidemic thresholds and post-epidemic thresholds, right? So this is just the first rough approximation of what can we define as baseline outbreak activity or outburst activity, sustained transmission, and back to baseline, okay? It's the first rough approximation on that. Now, what we get in this, when we apply this function, is, for MEM timing is the duration, actually, of this period. So it says that, well, it lasts about 10 weeks. And in terms of when it happens, it might vary the starting point from the row 14 to the row 23. So let's check what we have in terms of, so row 14 in our original data set corresponds to the week 1. Okay, why is that? Because when we changed our data structure into this object here, we lost the label associated with each row. Okay, so we now have, in this data set, FluSeal 2001, each row has only the indexes of the entries there is from 1 all the way to the size of that particular object, the number of observations, which is not the label associated with the occurring week related to that row, right? Because for this data set, remember, the season does not start at week 1, rather it starts at week 40. So when we say that, well, it starts at week 14, actually at row 14, we have to go back to our original data set to check, well, row 14 corresponds to which actual week, right? And for that case, it corresponds to the first week of the year of 2002, right? And row 23, it's week 10 associated, okay? So it lasts more or less 10 weeks approximately, and it goes from the first week of the year all the way to the 10th week. So beginning of January up to more or less mid-March, okay? Because week 4 is the end of January, week 8 is more or less the end of February, March will go from week 9, 10, 11, and 12. So week 10 on a yearly calendar corresponds to more or less mid-March. So if we check, what else do we have as outcomes for that particular object that the function MEM timing returns? So the duration, the accumulated number of the accumulated incidence. Now the timing is those two barriers. So the separation between, so the beginning of the epidemic phase and the end of the epidemic phase. And also, it also gives you what are the observed incidence in the pre-epidemic window and at the post-epidemic windows. So it's the observations, right, associated with that period in our time series and this period on our time series, So with that, you could make a first guess as well. We could then, so since an incidence of 39 point something, about 40 cases per 100,000 individuals might be our epidemic threshold right away, because it's the maximum incidence observed in the pre-epidemic phase for this particular season, right? Another way to go, which is what we discussed in our class as well, to take the set of observations there labeled as being corresponding to the pre-epidemic phase and analyze that distribution and calculate quantiles of interest or deviance from the mean or whatever. So in a way, use that as a distribution and calculate extreme values associated with that distribution. And that will be then our epidemic threshold. This is what we discussed in our last class. Yeah, go ahead. Remember, we just, we passed to that function only one season, right? Just the first one, from 2001 to 2002. So this is the observations associated with that season in the weeks that were labeled as being part of the pre-epidemic phase at that season, during that season. It's not ordered in the way that they appeared. Okay, it's not the first week of the pre-epidemic phase, the second week, the third, blah, blah, blah. No, it's just the observations. Okay. In fact, it's ordered in a decreasing way, and that's it, regardless of when they happen. Okay, just from the highest to the lowest value, and that's it. So, and this object, it's already one of those smart R objects. So an S3 object that we can, if we apply the function plot in this particular object, it already has encoded in that object a specific way to plot the values associated with that object, okay, which is this one. So we don't have to worry about structuring our plot unless we don't like that particular visualization. Okay, but if you want to use that just by calling the function, the R-based function plot, it already looks into the information, the underlying information in that particular object, and gives us this representation. So we have the observed values of incidence for that particular data set. So the underlying, the original data set that was used to construct that particular object. And the observations are color-coded, associated with what has been defined as pre-epidemic, epidemic, and post-epidemic phase. Okay, so the separation will be here. So remember, what we had was that the time in there, it starts at the row 14, ends at row 23. Now, since in the object that we passed to the function, we didn't inform it that row 1 was week 40, row 2 was week 41, and so on and so forth, it has no way of knowing that, so it assumes that the index is already your weeks. So it uses here on the x-axis the label week, because this is what it is expecting to receive in your data set. But the index are associated with what was in that particular object that we provided to the function. And in that object, we didn't rename our rows to accommodate for the fact that the weeks are from 40 to 30-something, okay? So it uses what it has. So it started week 1 all the way to week 33. So when we interpret this outcome, we have to remember that in this case, what we call the first week of the season correspond in the yearly calendar to week 40 and then 41, okay? And you can see that as was the output, said that, well, it attributes the beginning of the epidemic phase to week 14, to row 14, and the end to the row 23. You can see that the observations here that goes all the way up to the row 13 are coded as are labeled as pre-epidemic, and from row 24 onwards, post-epidemic. Okay, so it's exactly this process, just represented in a different manner. But instead of putting vertical lines separating each of those phases, the dots associated with each observation that carries that information directly. Okay. Now we can do the same thing for the data set associated with Germany. Okay, and now we have that for this particular object, we have already the labels in the object itself. So again, it returns the duration here of 9, in this case, days, right? Because our original data set is organized, aggregated by days and not by weeks. And it starts at row 27, ends at row 35, and then we go back at the row names of that particular object, and we see that, well, row 27 corresponds to the 25th of October, and it ends by the beginning of November. Now, as I've mentioned in the previous data set, since now the data that we provided has labels associated with each row, that information in the original data set is already used when constructing the plot, okay? The downside is that it is hard-coded to assume that the data set is aggregated by weeks, which for this data set is not the case. So the labels associated with times are correct, but the name of the axis, not so much. Okay, but this we can change easily. Now, when we can see, as we've seen in our last class, for this particular data set, this first passage of defining pre-epidemic, epidemic, and post-epidemic is not that good. So we have to tweak the parameters associated with the method. Because remember, I haven't passed any parameters. We just applied the mem timing function on top of it, so it's using all the default parameters of that function. Okay, and we've seen that in the last class that there's no such thing as one size fits all in terms of methodology to estimate or classify a season in terms of pre-epidemic, epidemic, and post-epidemic season. So what we would see clearly here is, well, the default parameters are not good enough. Even though this is we know that this is just the first stage of the process, it's still pretty bad. Now, for this function, by default, it uses what we called yesterday as method 2, and the reason why we use method 2 is because it's the number associated with the parameter for the method that you want to use in this function. Now, method 2 is the, as we mentioned yesterday, we discussed yesterday, we take the map curve, remember, which is the curve that we use to calculate the maximum accumulated percentage of observations for different window sizes, right? And method 2, what it does is, well, it calculates the derivative of that function and set a threshold for that. Whenever the derivative is becomes below that particular threshold, we say that, well, now this, from then on, we have the epidemic phase already, right? Now, for this particular data set, the threshold for this method, the default value for the threshold is a value of 2.8 for the derivative. And for that particular data, this is not at all good enough. Now, let's see how things changes and how we implement changes in that function. Now, this, the function mem timing accepts several possible parameters. One of those is the method that you want to use for providing that, for calculating that, that first passes, that first estimation, that first rough approximation of what is pre-epi and post. And so if I say I method, I call the function with my object, my data set, and specifying that I want to use method 1, we see now that there has been already a slight change in the outcome. So now with this method, it says that, well, the duration of the epidemic phase is 11 weeks. With the previous method, it was 10 weeks, so it's just a small change in that particular data set. The starting point is the same. So we just added another point here from the post-epidemic phase to the epidemic phase. Okay. Now, if we use method 2, so the first method that was used, but just changing now the threshold on the derivative, remember, the map curve was something like this, right? The bigger the window size, the bigger the accumulated percentage, and it saturates when the window size gets closer to the maximum of our season, right? Now, by lowering the threshold on the derivative, what am I doing here? I'm moving to the left or to the right in terms of window size, right? Because here is window size, right? The axis here. So, and this is always what the map curves looks like, right? The structure, it's always like that. It can increase a little bit slower than that. It can increase faster than that. But it always has this shape, this form, right? We've discussed that yesterday, right? Because the way the map function is constructed, it must look like that. There's no other way around. So the smaller the window size, so if we move in this axis to the left, what happens to the derivative of this function? It increases or it decreases? It increases, right? The map curve is a non-decreasing function. Its derivative is a non-increasing function, right? So if I lower the threshold, which is what we are doing here, the original value, the default value was 2.8. Now we are setting it at 2. What am I doing? I'm moving to the right. And what does it mean to move to the right? Is that, well, I want my epidemic phase to be larger rather than shorter. Because this is what it means to set a lower threshold for the derivative, right? Instead of setting it what would be corresponding to this point, and I'm putting over here or whatever, right? I will have to look at the, if we construct the derivative of this function, we would know exactly what it means to set different values in terms of window size. Go ahead. Well, it depends on the function. Depends on what the map curves look like, right? So it's a wild guess in the end. Well, not explicitly a wild guess, but you can think of that as what do you want in terms of the angle associated with the slope of the map curve? Because we are setting a threshold on the derivative. This is exactly what it means, right? But on how big it will be, well, depends on how these curves look like. If it's a rapidly increasing function, this if I set a specific angle, it will be over here. But for this other one over here, it might be over there or over here. Depends. There's no way to knowing beforehand. And most important than that, it will always depend on the season, how the season looked like, right? Because for each season, I will have a different map curve. A different map curve will lead to a different derivative of the map curve. So the same threshold means possibly different things on different data sets, okay? Well, we've just seen that. We went from a window that made sense for the first data set and didn't for the second data set. You, go ahead. Sorry? Yeah. Empirically. Yeah, that's just it. Because this is the only thing that you can say about your choice. What is the angle associated with the derivative of the map curve? Period. You can't say anything else, okay? Because what having that angles means for each season, your guess is as good as mine, okay? So by running, evaluating this method on different observations, they propose that, well, usually a good threshold should be between 2 and 4, a value between 2 and 4. And this is just an empirical result. You get a bunch of data, you run the method, and you do a sensitivity analysis. Well, if by changing the threshold, how my window changes, and how this changes better represents better or worse what I actually want to label as pre-epidemic, epidemic, and post-epidemic. How do you do that? You call a bunch of experts and you confront the outcome of your method with the opinion of the experts. You send them the same data set and you ask them to point out what they think, how they would label pre-epidemic, epidemic, and post-epidemic. And then you confront that opinion with your heuristic approach. Okay? Now, so it makes sense, right, that when we lower from 2.8 to 2, it ended up leading to a window slightly bigger, right? How big it gets, again, depends on the original data set. For this data set, it means adding 1 more week. Now, if we increase it, instead of lowering the threshold, I increase the threshold. So it was originally 2.8. First, we set it at 2. Now we are setting it at 4. What we expect on the chain for it to be shorter, right? Either the same or shorter. The opposite of what we had before. We lower the threshold. What we expect is, well, it either stays the same or it gets bigger. Now, the inverse. And in fact, now we go from the original 10 weeks to 8 weeks, as expected. Okay? And this is the outcome. So we see that for this particular data and this particular method, the delta parameter, the threshold on the derivative, the data set is not that much sensitive to that particular parameter because we can change it from 2 to 4 and the impact is quite small. Okay? Now, the same exercise on the German data set. Now, method 1, we already get a way better classification on your data set. Now, by changing the method used to label our time series. We moved from method 2, which was the threshold one, to method 1, which was that calibration of, well, grabbing the minimizing a function that is a combination of window size and the derivative of the map curve, right? Method 1 was that. We constructed the function, and that it was a combination of those two variables, and tried to minimize that particular function. And so this leads to setting up a different cutting point for the window size, and for this particular data set, much, much better. Now, if we still stick to method 2 and tweak the threshold, looking for a larger window size, because remember, how would we make those evaluations if we know that using this particular method based on the derivative, I use the default parameters and I get a window that is too small, and I know how the process works, what should be my next step? To increase or to decrease the threshold? We know how it works. We know what we got. We got a window that was too small, so I want to make it bigger. If I want to make it bigger, what I need to do if I stick to that method and just change the threshold? Should I make the threshold larger or slower than its original value if I want to increase my window size? This is exactly what we discussed before. What we got to do? Lower the threshold. Lower the threshold means the lower the threshold, the bigger the window. This is what we want to do, right? If the window, the initial window was too big, what we needed to do was the other way around, to make the threshold higher than what it is. because my window size is too big. Okay? This is how you use the information associated with the construction of the method on how you tweak the parameters based on the result that you got as a starting point. Okay? This is like the workflow associated with that. So by lowering the threshold, we expect and we get a larger window already. We go to, originally with 2.8, it was only 8 time units, right? And now is already 20 time units. Remember what I just mentioned about the sensitivity sensitivity associated, or sensibility actually, associated with fine-tuning that particular parameter. For the Castilla-Leon, didn't make much of a difference. I could change it from 2 to 4, and it doesn't really change that much. With this data set, the same change from 2.8 to 2 already has a larger impact on my window size. Yep. Yeah. The caution that I would take there is, well, my season might not be the duration of my season might not necessarily be 1 year. It might be longer than that. So what I define as a season could be, I don't know, 2 years, 3 years, whatever. Okay, so it's much more number of time units on your season than rather days or weeks. It depends on how fast your curve is changing. Okay, but yeah, the more fine-grained it is, the more observations I have in a given season, you expect at least for this method to be more sensitive. But also, not only that, and even probably more, well, it's associated with that as well. No, it's the same thing. Yeah, it's just the time scaling. So time scaling is the answer. So the size of your unit of time in respect to the size of your season itself. Okay. So yeah, a lot better, but still not good enough. And you see, remember, what was the suggestion at start? Well, your threshold should be between 2 and 4. Yeah, it might work out pretty fine for several examples. We already have here a counterexample. 2 is still not good enough. It should be even lower than that, because we need, for this data, for this season, the window size should be larger than that. This is still too narrow. So we should use a threshold that's even smaller than the proposed, suggested minimum value for the threshold for this particular method. Okay? Just to emphasize what I have been saying since day one, your data matters a lot. There's no easy approach. Okay? There's no golden standard, unfortunately. Now, if we move in the opposite direction of increasing the threshold instead of lowering it, it's only a peak. Okay? Which is as small as it can get. It doesn't get any smaller than that. Okay? So, both the minimum and the maximum suggested values doesn't make any sense at all for this particular data set. Okay, for the previous one, it was pretty good. For the Castilla and León data set, it was pretty good. Now, so in terms of the MEM package, now, so remember, this exercise is, as we've discussed, just the first step. It's the first approximation of establishing those phases on our data. What we want is that once we made this partition of our data, then we want to grab all the observations that we have associated with the pre-epidemic phase, or a sample of that, and build a distribution of those observations, and from the distribution of those observations, then calculate what is the epidemic threshold, or the pre-epidemic threshold, if you want to call it. Now, for this package, it doesn't allow you to calculate thresholds with only one season. Okay, even though with a single season, you might already get a good number of observations labeled as being pre-epidemic ones. It's still the method is hard-coded to not accept and not calculate epidemic thresholds if you only provide a single season. Okay? We know that the method itself doesn't care about it. All right? As long as you have sufficient observations here, even if it's from a single season, you can, in principle, calculate an epidemic threshold. Okay, the usefulness of that, it could be debatable. Well, is just one season really representative of what you expect to occur every given season? I don't know. So this is the logic behind not accepting a single season. But in terms of the method itself, there's no impediment there. Okay, you can calculate. Well, we did in fact calculate yesterday, right? With using only a single season for both of these data sets. Now, since I'm gonna here use the functions from the package itself, we will abide to that restriction and make way with the German data set and stay just with the influenza from Castilla and León. Now, as we've seen already, we have several seasons. So the commitment of having at least 2 seasons, it's already met. And now, instead of running the MEM timing function, what we're going to do is to use the MEM model function, which is the full process of the proposed, actually, workflow for the movement epidemic deaths method and in this R package. So this particular function will run the MEM timing. From the MEM timing function, it will then calculate the epidemic threshold, post-epidemic threshold, so on and so forth. It will calculate also the endemic channels in the way that we discussed yesterday. It is making a time shift in each season, so putting all of them on top of each other, aligning the beginning of each before starting to calculate the endemic channels and so on and so forth. So now, so the information on that object, if we just call the print function on top of that, it gives you just the fundamentals. Okay? So the pre-epidemic and post-epidemic thresholds, and what it calls the intensity thresholds. What are the intensity thresholds? Is, remember, we discussed yesterday that, well, I can use those two regions to calculate, to estimate what is a reasonable threshold for me to identify when things start to increase in a sustained way, and to identify when cases are already low enough that I can be assured that, well, the season has ended. Now, from now on, I will just observe baseline cases. But we can also use the full time series to identify, well, how, especially in terms of the peak of my season, how would I classify it? Was the peak of that of each particular season within expectation, higher than expected, or significantly higher than expected? How do I go about doing that? In the same way that we define the pre-epidemic thresholds based on those observations alone. Now what we do is, well, we build a distribution of all the observations that I have, regardless whether they are from baseline, peak, or again, baseline. And on top of that distribution, I will then calculate deviance from the mean, or quantiles associated with that distribution. Okay? So the proposed thresholds here, and I can set whatever I want, okay, as base of reference on top of that distribution. Okay? So by default, it defines a medium intensity threshold corresponding to the 40% percentile associated with that distribution. So it will separate what is, well, below, I expect to, at that value, I have 40% of all my observations being below that, and 60% of my observations being above that. Okay, so it's a reference to, well, what is more or less within expected, what is expected for any given week. Okay? You might say, well, why 40? Why not 50? Why not take the meaning of my distribution as a base reference? It's up to you. It's up to what we want to do with that information. Just that. Okay? Now, since usually we want to use that information to classify my seasons in terms of its peak, in a way that we can say, well, this particular season was extremely high or within reason or whatnot, what we want to look at is, in general, we want to focus at the high and very high intensity thresholds. And by default, it sets at 90 and 97.5%. Again, you can use whatever you want. You could use 90 and 95. You could use whatever makes sense for what you want to conclude, what conclusions you want to draw from it. And what the European CDC uses, how it uses that information, is that, well, if a given season, so I have, in a given season, I have if I cross the high activity threshold at least once, this is already a season classified as being a high activity season. Now, significantly high activity season, what I do is that not only, well, it says that they established what is that, well, if, of course, it crosses at least once the very high activity threshold, this is already enough for me to classify a season as being extremely intense. But also, even if it doesn't cross the very high activity threshold, but it crosses the high activity threshold for at least 4 weeks, if I'm not mistaken, still it is classified as a high activity season. Why? Because even though the peak itself was not an outlier, it stayed at a very high volume for way too long. Okay? Because the impact, it's also important. Even if my peak is not too high, but I had several weeks of large number of observations, the impact of that in our, not only in the health of our population, but also in terms of medical resources, is already high. So this is already important for me to classify it as a high activity season. Okay? This is how those two thresholds are used by the European CDC surveillance for influenza. Okay? Now, looking at the fine details provided by the function summary applied to this particular function, it tells you several important aspects for you to have in mind when you are reporting your results. So remember, we know that for the classification in pre-epidemic, epidemic, and post-epidemic, we can use several methods. So knowing which method was used is important, especially for reproducibility, right? If I don't know which method was used, I won't be able to reproduce the same results, because we have seen that the method is important. The results will change or are very likely to change depending on the method. So in the summary, even though you didn't specifically inform, it already tells you all the fine details. So number of seasons that were used to extract the results, the label associated with the columns, okay, of those seasons. So as long as the columns are named in an informative way in your original data set, this is what it will use, so it could be relevant. So naming your columns, if you want to use that as part of your report, already labeling your columns on a meaningful way could be quite useful. Now, how the confidence intervals were calculated or estimated for each of the thresholds, because remember, again, we are always going back to constructing a distribution of observations, and from those observations, estimating outliers or cutting points, right? So we must also define, well, what is the statistical method that I want to use to estimate quantiles on a distribution that I don't know what it is. I have observations of that, right? So by default, for the epidemic threshold, so how it will assume what the distribution of those cases look like, it uses just arithmetic mean and confidence interval. So underneath, the underlying assumption is that it follows a normal distribution. Well, does it? Not really, but it might be a good enough approximation. Remember, you don't need to be exact. You don't need your assumptions to be perfect, because you don't know, usually you don't know, and you don't have a way to know what is the exact distribution associated. So we have to look like what fits best and go with that, okay? Now, you can also use, and for at least some of the parameters, you can also use a non-parametric approach. That is to say, well, I won't assume, I will not be assuming a uniform distribution or a log normal distribution or whatever, which would be the case for the geometric mean. What I want to do is go for the median and quantiles directly with bootstrapping method or whatever, which is what we have that for the median and is two-sided. Those are all parameters that you can change when you call the MEM model function. Okay, I'm not going over the details because we don't have time for that, but just showing in here some of the aspects that you might change, and looking at the documentation for the function, you have the description of each parameter that you can change, what each change means, and so on and so forth. Okay, and for estimates that if you want to use non-parametric estimations on your observed values and calculate confidence intervals based on bootstrapping methods, you can also specify which kind of bootstrap method you want to use, how many iterations of the bootstrap method you want to use, and so on and so forth. So it leaves a lot of room for fine-tuning, okay? And why is that? Again, because it matters. And there's no way to knowing beforehand what are the good parameters. You will have to fine-tune it. You will have to run it until you find what fits best in a model. Of course, don't go around checking all of the possible changes. Go step by step, and once you get a result that already is well representative, is good enough, it's good to go. That's it. Okay? Don't, again, as I've mentioned for some of the groups in the discussions, the same thing that I mentioned in the exercise here for the groups that don't overcomplicate your work, the same thing goes here in practice. Because again, the exact thing do not exist. Okay? Now, and then the proposed visualization of the outcomes of this particular function, it gives you in the left when it defines pre-epidemic and post-epidemic windows, right? The epidemic threshold here, and it draws all of the provided seasons, but again, already shift in time, okay? This is important when you're analyzing this output. This is not for, you have no guarantee that for each of those seasons, this is the week when it actually happened, because the seasons here have been shifted. Okay, some of those seasons might have stayed the same, because the starting point here is exactly coinciding with what was estimated for the whole set of seasons. So it will be the reference week, and so those will not be changed. But for weeks where the epidemic phase was set earlier or later than what was defined for the whole set, those seasons will be shifting time. Okay, we will see in a short while this in the data, how this reflects in the data set because it also gives you this output. On the right-hand side, what you have is the expected curve, okay, based on this construction, already shifting and building those intensity levels week by week. So it's here the median associated. With all the thresholds, the pre-epidemic thresholds, with its value, post-epidemic, the medium, high, and very high activity thresholds, okay? And you can extract those informations, several of those informations, in the in your object. So here we have what is the expected values for the starting point of the seasons, and it says as well, and with the confidence interval associated with the week assumed to be the starting point of the epidemic phase. So it says as well, my best guess is that it starts at observation 12, which corresponds to week 51, but it could also start at week 42 or at week 2. So this is the range associated with the estimated week for the epidemic phase to start, okay? And again, this confidence interval you can tweak in the parameters as well. So what is the window size for the confidence interval that you want to use, okay? Now, so this is it. Let me go back to so when you look, so one of the objects that it provides you within the output Flu-Silman model is this, what it calls the moving epidemics, which is exactly the original seasons already shifted. So what was the shift implemented in each season, right? So exactly now, so you know that, for instance, the third season here, you can see that all the, several of the first rows are now NAs. Why is that? Because this season was shifted to the right. And what does it mean? Recalling what is the construction here, what is the system doing, is once it defines from the set of all observations what is the most likely week as the starting point reference for the epidemic phase. Once it does that, it goes back to all of the seasons and check, well, for this season, the reference week is this one. But for the whole set is here. So what I'm going to do is take this season and shift it so that they coincide. So for season 3, what happened? The epidemic phase started earlier or later than my reference from the whole set of seasons? Later? If it was, let's see. So I have, put it up. So let's say that this is a particular season, and for that season, the model estimated that this is the starting point for the epidemic phase, and for the whole set of seasons, my estimate is over here, okay? So the moving epidemic idea says that, well, now to compare this season with what I expect to observe, the first thing that I'm going to do is to make those two coincide. So if this is my reference for the starting of the epidemic phase, what I'm going to do is this time series, I'm going to shift it to the right, which is what happened there, right? The fact that it has a lot of NAs is because, well, if I move this season to the right, if I move it 3 weeks, for instance, what will be the value of the first 3 weeks of this shifted season? I have no idea. It's NA. This is why it's NA, okay? Because there's no observation associated. So by looking at where the NAs are placed, if it's rather in the beginning of the season or at the end of the season, I know what happened there. Since it has NAs in the beginning, it means that that season had to be shifted to the right. If it was shifted to the right, it means that it started earlier than I expected. Okay? Now, if I had another for season 5 here, what I have, it's something like that. Because that particular season had to be shifted to the left. If it was shifted to the left, it means that the associated epidemic phase started later than what I expected. Okay? Now, there are lots of things to go over, and of course we don't have not near enough time to go all over them. And I want to go over our surveillance data to discuss a little bit the particularities. This part I'm just going to finish by showing you what is the output of the documentation for the dysfunction MEM model from the MEM package. And you can see here this whole plethora of arguments that you can pass to the function, as I was mentioning. So you can, even though you have, let's say, 20 seasons, you can specify how many of those you want the method to use for the estimations by the argument I seasons. You can change the type of confidence interval associated with any estimation, the method used for those for the map curve. So Y method is what it says that optimal timing of epidemic, so it's associated with the map curve. The level threshold is, again, what are the the confidence interval that I want to use for the pre-epidemic threshold and for the post-epidemic threshold, because remember, I will have a distribution of observations, right? And for the pre-epidemic threshold, what I want is kind of something like that, right? Well, what is that? Is the 95 percentile associated with this distribution? Is the 90? Is the 80? It's up to you. And it's controlled by that parameter, I level threshold. It's where you want to put your barrier here. So how much of an outlier you want it to be from your distribution of pre-epidemic observations to set your pre-epidemic threshold, okay? Now, there's lots and lots of things. This is something that if one want to use this method is to sit and go over the documentation. Now, to wrap it up, let me show you here. So in Brazil, fortunately, so we have lots of open data sets from our health system. One of those is the Open Data Source platform. So, and this is quite new. It started. This initiative started in the pandemic. Before that, the main source of data was TabNet, which has data on several diseases that are notified. The issue there is usually related to how updated that data is, so when it is released to the public, because several of those take quite a while for them to close the data and make it public. So for using on for real-time analysis usually is not good enough because they are not updated on a weekly basis or not even on a monthly basis. Some of those data sets are only updated once a year. Okay, it varies from data set to data set. But for for the severe acute respiratory infections, which is the system associated with the notification system, it's called the CVAP gripe. This data set in Brazil, we call it ISRAG, which is severe respiratory síndrome respiratória aguda grave, which would translate to severe acute respiratory syndrome, but it's not that because it would lead to confusion with coronavirus specifically. So it's SARI, the associated. We have here now the data from 2021 to 2024, 2020, 2009 to 2012, 2019, and 13 to 18. Any guess on why is it separated like that? But then why 2009 would be separated, would be cut at 2012 and then from 13 to 18? And why 2019 would be separate as well? This is part, but it's not all of it, but it's part of it. But also because the variables changed. So you don't have a consolidated data set, a common data set from all the way back to 2009, all the way to 2024. Because the database itself is different, okay? Wait? Well, during the pandemic, they changed the definition because of some particularities to make it more, to broaden the range of the syndromic surveillance so that you would catch more cases, so that we're more likely to not miss any COVID-19 cases. This was the reason here. And at some point, there was during 2009, but then it doesn't affect the change from 2009 and onwards. During 2009, there were some changes at the beginning because it started as focusing on the H1N1 pandemic, and it started as all cases. Then it restricted to just hospitalized, as now it is. Because before that, the surveillance of SARI cases in Brazil was restricted to intensive care units alone, and sentinel units on intensive care units. So this database before 2009 was even different. Well, from then on, it's supposed to have all the hospitalized cases. Whether it does have it all, not really, but you can assume that it does. But the idea, at least, it is that it is. Okay, But then there is this fact of, well, how you want your syndromic surveillance system to be more sensitive or more specific. So this is a reason to reevaluate your definition of case from time to time. As I mentioned, there is an ongoing discussion, a worldwide discussion, whether fever should be a mandatory symptom for severe acute respiratory infection surveillance. In Brazil, it's no longer the case. It used to be. Now it's not, and it changed during the pandemic, because especially in the elderly, not all respiratory infections lead to fever. And since this was the most affected age group during the pandemic, to keep that restriction, you would lose a lot of cases. So let's make do with that symptom. Okay, it's still part of the possible symptoms, but it's not a mandatory symptom anymore. Okay. Now the changes here, most of them are not associated to. In fact, I think all of them, except from 2020 onwards, is not. It hasn't to do. It's not to do with case definition change, but database change directly. So what are the variables that are present in my system, in the database? And if that wasn't enough, some variables change the type of the data. So it used to be represented, for instance, as a name and change it to be a code, and the other way around, a numeric code. So, but fortunately, once you enter in the specific link to each of those, you have not only the database for each of the years associated, but you have also, and maybe more important than that, the dictionary of variables, so the metadata. Okay, and you have also the notification sheet, so that you have an idea of what is actually being done at the healthcare facility, right? So this ficha de notificação, it's the paper sheet for the notification. So this is what is the first step on the healthcare facility to fill out this form, and from that to upload then to the database. And so if we go here, let's see, for 2013 to 18, let's see what we have here. So you have a number that is associated with the notification. So you might think, so, well, this is a unique identifier for all notifications. It should be, but in reality, not so much. It's at the end of the day, it's not a unique identifier of each notification. You have some notifications that share the same number of notifications. So to separate, actually what you have to do is at least combine the number of notifications, so this variable, with the municipality of notification and the date of notification. Okay, with those three variables, then you have a unique identifier for each entry on this system. Okay? Now, so you have information on so the date of notification, the week associated with that, year, the federal unit or the state or province where that case was notified. And you can see that you have later on this other variable here is also associated with state or federal unit or province. Why is that? Because this one now is associated with the state of residence of the individual that was notified. So it's one thing to know where the case was notified, and another thing to know where that individual comes from. What is his place of residence? Because you can have an individual that lives in a given city, but he's hospitalized in another one. Okay? So again, depending on what you want to do, on what you want to analyze in this data set, you should use one or the other. Because one will be related to where the cases are being observed, and the other is where it is also likely to have occurred the infection, in fact. Right? And you have that also, so you have for the, of course, for the province, you have here the information regarding the city, and then the age of the individual. There are some variables here that are in the full database, but not in the data that is made public. For instance, the neighborhood of residence of the individual, the street address, and so on and so forth. Why those variables are not available in the public data set? Because these would make it possible to identify the individual. And this is something that you can do. Public databases should be anonymized. You should not be able to identify individuals in a public database. And with those, you could. So this is why they're out of the picture. Now, what about as we said, we know that this is a syndromic surveillance, right? So it might have influenza cases, COVID cases, so on and so forth. So if you want to stratify your data set based on the actual pathogen associated, one possible way is to look at, well, did this individual had a PCR test associated with this case? So the PCR variable tells you exactly that, whether this individual was tested or not through a PCR testing. Before 2018, we had a lot of cases that were tested by immunofluorescence testing, not PCR. So some cases might have a lab result by what is called here IFI, which is immunofluorescence. Okay? So if you want to have all the cases that were positive, let's say for influenza, you should look both at the PCR result and the immunofluorescence result. Unless you want to restrict yourself to a specific test. No, I want only those that were tested by PCR. Okay? And you can do that for all the possible outcomes. And then, of course, this is just telling you whether the individual, that particular case, was tested through this method or the other. And then you have the data associated with the PCR. And then you have, well, was it positive to influenza A? If it was positive to influenza A, was it subtyped? And if it was, what was the subtype associated? Was it the H1N1 pandemic? Was it seasonal H1 influenza, H3? It was not subtyped. It's H3N2 or another subtype. So I had a result, but the result is not any of those. Influenza B, RSV, parainfluenza 1, parainfluenza 2. So we have several columns, each of those associated with different pathogens. Important thing here, although it has the possibility of having either positive, negative, inconclusive, or not tested, what we see in fact, it's only if it was positive or not. So you either have one or nothing. What does it mean? Can I be certain, for instance, if I look at one entry and I see that it's marked as positive for influenza A, let's say, can I be certain that this sample was negative to RSV or to influenza B or to SARS-CoV-2? As long as it isn't explicitly specified that it's negative, you don't even know if it was tested for that pathogen, let alone know if it was positive or not. Why is this important? Because if you want to calculate positivity, for instance, you need to know how many cases were tested, in fact. And what this database tells you, it's only whether it was tested with PCR or not. But for what pathogen, it's not there. You only know those that were positive, or if they have explicitly mentioned that it's negative. Okay, so that one I know that it was tested. But usually what happens, so several states run multiplex PCR testing, which means that for the same sample, they run on a single shot more than one pathogen for testing. So influenza A, influenza B, RSV, SARS-CoV-2, so on and so forth. But what goes back to the database is just which of those was positive. So we have no idea what was tested or not. This has an important impact on what you can do with that database, okay? Because you only know those that came back positive. You don't even know what was tested, in fact. This is a limitation. This is a very important limitation, okay? Since we are already way far ahead on our schedule, I won't dwell much more on it, but just some final remarks here. You have the final classification as well, which tells you for the data from 2013 all the way to 18, whether if it was classified as SARI by influenza, SARI by other respiratory viruses, SARI by other etiological agents, so not respiratory viruses, and unspecified SARI. So those that you have no clue, based on testing, what is the associated pathogen, okay? But this is not, that alone is not sufficient for me to say whether this is a confirmed case or a probable case. So we have suspect case, we have probable case, and we have confirmed case. The suspect case is all of those that meets the syndromic characteristic. So they have all the signs that it's likely to be this or that disease. And of course, based on symptoms alone, you might have a whole set of possible diseases, right? So it is suspect for several diseases. Here we're just looking for SARI. Now, a probable case is those that not only meet the definition based on signs and symptoms, but also share an epidemiological link. So for instance, you have, you know that it's associated with a region where you have confirmed cases. You know that there is an epidemic of influenza A going on, and you have suspect cases of influenza, you might say that those are probable influenza cases, even though you don't have lab result yet. Okay? A confirmed case are those that have been tested and came back positive. If you don't have a lab result, strictly speaking, you do not have a confirmed case. At most, you have a probable case, okay? But most likely, you have a suspect case, confirmed only by lab result. So with the classe final here, the final classification, it's still not there, okay? It's telling me that, well, this is a SARI influenza case, but I'm known, with that information alone, I don't know if it's whether a suspect SARI influenza, a probable SARI influenza, or a confirmed SARI influenza, okay? So you either go to the columns of lab result, or you can take a look at the column criteria over there. The variable criteria tells you whether this final classification, from where did it came? From a lab result, from a clinical epidemiological assessment, or just a clinical assessment. This is exactly that. Now, this gives me the answer, whether it is a confirmed. So confirm if the criteria is equal to 1, because it's lab result. If the value there is number 2, means that the diagnosis was based only on clinical epidemiological assessment, not through lab result. The most I can say is that this is a probable case, not a confirmed one. And finally, if it's only clinical, this is still a suspect case. Okay? So this is ways that you can separate that information. Finally, you have evolution, which means whether the individual became cured or died. And you have several columns associated with dates. So the date in which this notification was closed, date of the evolution, or date of death, and so on and so forth. And also, just to finalize here, you have, so we have several variables associated with preconditions. So if individual has any pneumopathy, cardiopathy, if it's immunodepressed, and so on and so forth. But also you have variables associated with the symptoms. So those, for instance, fever, coughing, throat, dyspnea, myalgia, saturation of oxygen, respiratory discomfort, and so on and so forth. So those variables are the ones that you can use to filter out your data, whether they are actually in accordance to your case definition or not. Because remember what I showed you in the first day, being inserted in the database is not in itself already a guarantee that that particular case in fact meets your definition, your case definition, okay? But since the variables are there, you can filter it out. Of course, there might be cases where the individual actually met the case definition criteria, but whoever was filling out the form didn't cross out the symptoms. Well, too bad. Okay? Again, depends on what you want to do with this information. You might assume that, well, if I'm only interested in burden and analyzing the situation, it doesn't matter if they actually fit the criteria or not. As long as the person at the healthcare facility thought that was important to include this case in this database, I will assume that this is a respiratory case that is relevant to the surveillance and be done with it. But if I want to assess, make assessment on risk, on the epidemiological characteristic of the cases, then it might be better to restrict myself to those that do in fact meet the criteria, okay? So that I don't insert spurious data in my analysis. Okay? Good. So of course, final step here, of course, would be to download this data, filter it out in any way we want, and also, if we are using data that are from different timestamps, we've seen that, well, we might have to accommodate the variables there. We might need to do some homogenization of the information because the variables have changed slightly, okay? This is something that is done post facto by whoever is analyzed the data, okay? Good. So this is it for my part, at least, in terms of classes. This was the last class from me. I will still be here with you, joining the discussions for the group activities and the presentations by Sunday as well. But in terms of classes, this was it. I hope you enjoyed it. I hope you learned something with it. And most important than that, at least from my side, is that I was able to at least give you a flavor of something, some pitfalls, some obstacles, some traps that are present in this endeavor. Okay? If you want to track this, and I encourage you to track this field of activity, be aware of what you're doing, of what are the underlying details of your data, to avoid drawing out conclusions that are driven by different aspects that is not exactly what you are trying to measure in the first place. Okay? Thanks a lot for your attention.